microscopic level. So another image is basically cerebrovascular disease. So what is in this one? It basically affects the blood vessels and the blood supply to the brain. The problems like basically the stroke, जैसे हम कहते हैं कि आदमी को से नस फट गई, ट्रांजिएंट ischemic attack, neurism. These type of problems are basically, again, they can be detected with the help of the this image only. See, as I told you, कि जैसे ही किसी को हम कई बार हम कहते हैं कि brain stroke आ गया, this brain stroke from the symptom it is visible, but at which we can even the general things can be done based upon the general symptom. But what has to rupture out? Which vessel has actually broken? Which blood vessel has broken? So for that part again the image is required. Degenerative disease. In degenerative disease, what we say it is progressive deterioration of tissues, organs or functions over time. Alzheimer's disease, Parkinson's disease, Huntington's disease, multiple sclerosis. So again, see these diseases also, if you want to diagnose them very clearly, it requires the image. In the neurodevelopment disorder, it affects basically the development of the brain and the nervous system. Here, autism spectrum disorder, these type of problems comes up. So there also you can see the basically role of the image. So when we talk about basically statistical studies of neurological diseases in worldwide and India, see why are we talking? See, as you would have observed, so there is basically shift in the disease. Earlier we say the basically the chronic disease, the other type of disease was the problem. But today, if you see what we observe here, that the brain stroke cases, basically in new cases, it is 1.2 million. That is basically this is the case. It is brain tumor. It is 28,000 in the worldwide. It is new cases. Alzheimer. It is a new. So if you see the new basically the growth rate is very in these type of diseases. So if we are not addressing these diseases from the beginning only, then it would be very difficult. So when we talk about basically the brain imaging techniques, see why the brain? See, because in brain, if you really want to go into the detail, the main thing is your image only. It's already a very complex one. When we talk about basically the 4 types of images, brain images can be find out. One is basically magnetic resonance imaging, computed tomography, functional MRI, positron emission tomography. Which is positron emission tomography is very popular in the cancer detection. CT scan, MRI are basically popular during the other normal disease. Just a minute. So these are basically the cases. So, MRI, remember functional MRI and MRI, very minute difference is there. It is basically based upon the level of oxygen. fMRI detects the level of oxygen in a MRI. Another image, see here even X-ray is also image, but here we are talking about the basically brain imaging technique. even see for why does the brain imaging only matter? If you really see, today see our main focus when the research is going on, because brain is the most complex part of the human system. There when we have to take the decision, whatever the study is there, whether it is, for example, if you are seeing some movie, whether the blood flow has increased, some vessels. So that way we are able to see the effect, different effect through the fMRI. So this is the, now see one very important thing, as I told you that in the medical image, it is not only a two planes, horizontal, vertical, but it is three, one here. What, how do we observe it? It is first basically it is a coronal basically at a we say vertical level, axial which is basically at a horizontal level, sagittal which is at a Z plane, and a lateral view what we say. So all see we don't know which view will be useful when we are basically seeing doctor have all the views available. So here also it's our so we should be aware, because many times in the data set we हमें क्या पता होता है कि हमें see this type of image is given, this type of image plane is given. So you should be very clear that at which level they are talking. So clear. So coronal is basically vertical view, front and the back view. Axial is basically the horizontal view at slice level, if you ask, and the sagittal is basically the lateral view. This is the imaging plane. Now you see what are the challenges in the traditional diagnosis. Reliance on basically the manual analysis of medical images like MRI, CT is time intense and prone to human error. If you would really recall, see who performs this thing, radiologist. A dedicated person is there who sees the image and make a report. And doctor then actually many times it depends. Then doctor actually first see the report, and if he finds something still confusing or not very clear, then he may or she basically see the medical image also. So what we are saying that remember it is prone to human. Why? Because you can really see the image. It's not it's not very basically preferred type of image. Where see only two shades are there. One is black, another is almost light black. But we don't have the choice. Whatever image is there you need to find out the information. So subtle patterns in these images may not be visible to the human eye. So that's why we are saying, that's why the subtle patterns are very difficult. Even see the when the radiologist is watching the image, see easy symptoms or we say the general symptoms are visible, but some specific symptoms, because remember if you are missing out some symptom, it is becoming a problem. It will become a problem because you have left the any sign of disease uncared. That's why the combination of neuroimage and ML machine learning not only enhances diagnostic accuracy but also reduces the time and cost of clinical workflow. See, that is also the because there is a long queue, etc. But if you see, really go to the government hospital, you really go to the government hospital, see, lot big line is there. There you need to give the reports, etc. There it becomes very essential to using these type of software. It bridges the gap between vast medical data and actionable insight. So that's why, but key thing here in the medical image is that it is here very limited images are available. because again it becomes an ethical issue. You can't share one data, another data. So making a data set, using that data set, that is also becomes very sensitive issue. And even see one thing, also you should be very clear that in medical images, when we are performing our analysis on the public data set, see we have very limited knowledge. But when you have the our own database, or we say the database that where we have other information is available, then it is your research is far more enriching than the normal research, right? Our purpose is not to get the C accuracy or 9899. See, for paper wise, it is okay. But when you really want to correlate the symptoms, correlate the new patterns in the images with the actual symptom, then your own database is required. So what you are seeing here you are seeing the images basically again. These are the different views are given here. Again, there is the sagittal view, clear view, coronal view, axial view. Now, see what the motivations, brain diseases such as brain tumors, Alzheimer's, and strokes are rising globally. Traditional methods such as visual analysis of medical images rely on the experience of radiologists and clinicians. As we discussed it, it depends upon. But any simple mistake can lead to a very fatal error. Neurological disease often present subtle signs that may be hard to detect in early stages. Access to specialized healthcare resources such as expert radiologists limited in certain regions, especially in rural or and underserved areas. You will observe their radiologists hardly comes because patients are not many patients are there. Then also there comes issue. Machine learning allows for the integration of patient-specific data to tailor personalized treatment plans. So here we are saying that again we are emphasizing machine learning only because here your data is limited. So that is there. But even we are saying that it is when we integrate the patient-specific data, then it can be tailored to personalized treatment plan. That where should I go through with. So here what has been shown here, see basic approach to analyze the brain MRI image, different data collection methods is there in the form of publicly available data sets and the local data set. Yes. So this is there. What means what type of frame, what type of view you are taking. So whether you are taking sagittal view, coronal. So it should be uniform. It should have the some standard way. Even see when you would note down the research, even these days when we see it, see we are saying that we are really at the developing level. But when you see, for example, my student Suman has been doing the research on the brain related data. I hardly see any Indian data. I always see the basically data from the some it is from the US, Europe, or even the uh, China, etc. Even see when my other student Ram Nivas had been doing work on the EEG and the last only 2 3 years before some data using in the from the IIT has come in the EEG. So this is very much required at our level. Data collection methods and the use of our data sets. Despite so many researchers, why are we lagging in basically generating the publicly available data sets. Various pre-processing methods such as contrast enhancement, noise reduction, RGB to gray conversion, data augmentation and segmentation. So, see, what do you mean by pre-processing? Pre-processing means, see, I need to process in a way that my then process data is ready to apply, means there I can readily apply my algorithm. So that's why we are saying it is a contrast enhancement, noise reduction, because noise has no role in providing the information. RGB to gray conversion, data augmentation and segmentation. See, many times it is, I don't need to apply the algorithm in the complete image, but on the specific part, there segmentation is required. Different categories, thereafter, see, then we different categories of features using various feature extraction methods. So as soon as you apply the algorithm, your image pre-processing has been done, then you extract out the feature when your algorithm is applied. After feature extraction, whatever you get, remember your feature length of required feature vector length may be large, then I should able to reduce it. How we are able to reduce it? Because we know, see, what information is really relevant in that overall feature. So, feature selection, feature sampling, dimensionality reduction techniques, PCA already we have done it. This is one of the techniques. Other techniques are also there where we can select out. Result analysis method. This is in the form of classification algorithm and statistical tests. So what see this is overall for the neuroimaging. The basic steps are there. Two approaches are available to perform dimensionality reduction. One is basically creating a subset of new features by combination of the existing features. And another is feature selection. It is a process of selecting a subset of relevant features, which is more informative to use in model construction. So what is the basis of your selection? See, again, the basis of your selection in keeping view of the objective, right? For example, I feel it, for example, that the tumor I need to identify, and the tumor is at the, we say the large intensity value. Then we can put up some threshold, and then we can, on that basis, we can select out those pixels where the intensity is large, then threshold. Another reason for feature selection is reduced computational complexity. It reduces overfitting and increase generalization capacity of the model. So here it has been shown that it is feature selection that already it was X2, XN. XN is there. Here we have reduced to the IN. So this is the one. So what is feature selection? If you see here, so this is the again the X only. But if you see the really the feature extraction here, algorithm has been applied and it has been changed actually. That's why it has been saying Y1, Y2, YN. Yes, it may be equal to the same length. It may be lesser than the actual original length. But what is important here is that here it's a transformation. Here it is showing that some function is applied, some algorithm has been applied in the feature extraction. So regarding the literature review, even see we have gone through it, but put up the things in the same context. We have shown it that the features gray level co-occurrence matrix is helpful in the brain tumor detection in the paper at the 32 number, their mean standard deviation variance has been taken. GLCM. GLCM, again the degree level co-occurrence matrix with the local binary pattern has been used to the for the Alzheimer detection and as well as the multi-class brain tumor detection. Then thereafter graph autism spectrum disorder that has been used in the graph Fourier transform and the graph convolutional neural network based upon the lines of the CNN. This has been done. So discrete wavelet transform, here you are using pathological brain disease detection, GNN, GFT. GNN, we will do it, GNN and GCNN both are basically the same. Here they are using for the brain tumor detection and it is the Alzheimer detection. So we will see the different thing. Now we come to the another part, see in the feature extraction, it is the GLCF, it is gray level run length matrix, which captures the spatial relationship between pixel intensity. Now we are coming to the capturing the relationship, right? Improving the discrimination between normal tissue, benign tumors, and malignant tumors. What is really the disadvantage? Disadvantage is require predefined parameters to compute features, struggle with representing complex structure or irregular pattern, operate on a single resolution, and do not naturally account for hierarchical or multi-scale structures in mind. Now coming to the LVP local pattern, histogram oriented gradient, Gabor filter, focuses on local patterns and texture and gradient information and rotational it is invariant. What do you mean rotational invariant? Even when you are rotating it, it points where the dimension will not change. Suffers, but what is the problem? It suffers in capturing the global relationship, structural dependencies, and the complex topological features of the brain. Then there is a shape-based feature. Here, see you what type of features you are using: area, parameter, circularity, gyratic movement, hue movement. These basic geometric features are useful for analyzing the size and shape of lesion invariant transformation. It is sensitive to noise and small image distortions. They might not capture the complex and intricate features of brain MRI image, not effectively capture very fine details, or highly irregular. Now, see, as I earlier also discussed that you can basically put up the different combinations. Yes, definitely on one hand it will increase the processing, but on later hand you are also able to know the some new observation. Combining LVP and Gabor filter allows the system to accept both local texture information and frequency-based feature. Able to capture fine-scale textural information from LVP and GLCM spatial edge-based information from HV and frequency-based features from the graph. So in a GLCM, it's shape-based GLCM plus this one LVP, HV, here it combines texture with geometric shape information. There's deep learning models that capture both low-level features and high-level features. Combining these features can provide a richer, more detailed understanding. So now coming to the family of transforms, and family of transforms is basically the again see it is what we have seen, which are so what is the role of these things? These are basically the feature extraction method. So DWT is basically easier to implement than CWT, a series of low and high pass filters are used to study the image at different scales. DWT is the most commonly used feature extraction technique. choosing the correct choice of wavelet is a tedious task. Struggles with irregular complex shapes like tumors, especially the tumor has non-uniform boundaries or significant texture variation. Empirical wavelet transform. Highly adapted to local structures, especially variable best feature. DWT focus only at specific scale, but EWT focus on. So empirical wavelet transform is highly adapted to local structure for edge-based DWT while DW specific scale. EWT focuses on variable, is computationally intense. Works well in low contrast region of the image as it enhances key features like boundaries through edge-based decomposition. Coming to the deep feature, definitely when data is available in the abundance, then it can be used. What is thing? It requires its disadvantage. Yes, it requires the more computational resources, long training times, neural network-based feature extraction can be overly dependent on the training data and structure with generalization. So here, what is the advantage? Here, the advantage is the it extract detailed features through deep layers. You don't need to tell basically the what feature extraction algorithm. You don't need to specify in the deep learning network. So it's almost alternative to a signal processing. It's becoming alternative that people have simply train the data. They train the data and then learning. But it has found out some difficulty encodes both the presence encodes both the presence and orientation of features, resulting in more informative features. Performs well on large scale data sets like ImageNet, making it a strong feature extract. Another deep learning basically very much used basically is CNN. CNN transfer learning. CNN automatically learns hierarchical features around raw data, eliminating the need for manual feature engineering. Transfer learning allows leveraging knowledge from large data sets, making it effective for small data sets. Here, what we need to do, find relationships between parts of the image are based on just spatial proximity, not on the feature similarity. CNNs are less interpretable and the learned features are difficult to understand. CNNs need large level data sets. So now coming to the part in feature extraction, it is a graph Fourier transform. In graph Fourier transform, as we already read it obtained from the eigenvectors of the Laplacian matrix of a graph signal represent signal into a vertex in graph spectral domain depends on Laplacian eigenvector. What is the problem? Problem is basically identify the right graph structure, identify the right frequency representation of graph signal. The graph structure means basically see what should be the structure, what type of, because first initially it is the person who is trying to find out he uh, is wants to fit into the some structure. So there it is clear, there you can take it as graph. But numbering, etc., all these are not very straightforward. So that you need to keep it in mind. Identifying the right frequency representation. Right frequency representation can be done, but here the main emphasis is the that sequence. Then in spectral graph wavelet transform, in SJW, scaling functions extract information from the spectral decomposition of the graph Laplacian. Scale basically, what scale you are using, what base you are using. It is simpler than traditional wavelet. SJWT offers better management on the selection of wavelet scale. Again, here say it is whenever it is graph is there, so graph structure and right filter is a matter of concern. Graph convolutional neural network. Remember, you have already see how the basically data is transmitted from the sender to the receiver. In the GSP also, we preferred it because it captures local relationships and can be extended to capture local dependencies through multiple gates. Unlike traditional neural networks that assume regular data, GCN can handle irregular structured data like social network, citation network, point cloud, where the graph connectivity may be sparse or dynamic. Training on large graphs can be computationally expensive due to the need to aggregate information from neighbors in each layer. The performance of a GCN heavily depends on the graph structure and how well the graph represents the relationships in the data. So, at the classifier and algorithm level, we have basically listed, because even you use the GSP or you use any other algorithm, these are the key things. So, that in keeping into that point, we have listed all of them here. So regarding the KNN, it can be used to solve both classification and regression problem. What K value you are taking. It may be 3, it may be 5, 7. It is very simple to understand and easy to implement and debug. Poor runtime performance if training set is large. SVM. Find a hyperplane that best divides data set into two classes. It provides good generalization. Performance is more than other linear classifiers. High computation complexity, it preserves the complex structure. PCA. PCA is used for the dimensionality reduction unsupervised learning algorithm. It reduces the dimensionality of data without important loss of information. Here, the data is linear and continuous. For complicated manifold, PCA fails to process the data. So, in LDA, it is used for the dimensionality reduction, linear discriminant analysis, and supervised learning algorithm. LDA is a simple algorithm that does not require extensive hyperparameter tuning like more complex algorithms. LDA assumes that the features of each class are normally distributed, which is often not the case in real world data. CNN is basically used for the brain tumor detection. Right? What does it do? It automatically detects the important one feature without any supervision. CNN models can't capture the feature of irregular non-Euclidean structure. What is the way? Again, see the GCNN is used. GCN provides the alternative that it can work on data with underlying non-irregular structure. GCNN include brain tumor detection, glioblastoma progression, multiple type lower grade glioma classification. So what we are saying here that the data where the irregular structure is there GCNN provides a very good. This work has been applied, and regarding the ANN, it is used for classification. It can model complex non-linear relation between input and output. It requires a large amount of labeled data for effective training. So, can we summarize it, our overall literature survey, when we are talking about the technique, different techniques for analyzing the medical? See, key thing, remember, in the signal processing is basically the feature extraction. Whole work of the algorithm is to extract the feature and thereafter feature selection. Feature selection is basically more or less governed by the machine learning part. So it is important part for preparing a testing environment. Based on variety of literature, graph signals in many different engineering size fields, GSP used in Alzheimer detection, brain tumor, glioblastoma progression, multiple type, lower grade, glioma classification. Majority of work performs on daisy detection, classification of emotions, sensor network, image and video sequences, biological. GSP has been introduced to extend the knowledge, see whatever things we are doing on the regular structure that can be applied on the regular structure. And in the analysis and processing of data that resides on a structured yet non-Euclidean spaces like social network, sensor network. As mentioned in the section other graph matrices, it is not clear why should we use, whether we should use the normalized graph Laplacian, unnormalized graph Laplacian. Which one is better? That these things are still to be explored. Even when you will see that paper which we referred day before yesterday, in that paper many challenges are there, many open challenges are there that you need to see. Though some would be there which would have been solved, also please go through that development. Some are there which have not been solved, try to take them as problem. Then later data clustering and feature reduction can also benefit from tools developed under the GSP framework. It has been used for the data clustering and feature reduction. Graph Fourier transform have been used to reduce the feature. So here we will take a small break. So just check out if you have. Just see whether have you any question. Just have a look over it. So see, one announcement also that in the like yesterday I mentioned you today see in schedule it has not been updated, but And the afternoon session will be taken by the Dr. Jyoti. He is basically working on the brain-computer interface. He has applied the different algorithm of signal processing to solve the different problems. So that will begin from 3 o'clock today. So now we come to the part C, methodology. Overall methodology, when we see it. Methodology means complete picture. When we are taking the deep learning, machine learning or the graph processing approach, all they work upon the neuroimaging data. The deep learning pre-processing is not necessary. In ML and graph processing, it is integral part. In deep learning, it is followed by the automatic feature extraction and then classification using DL. Please note the word automatic. More and more data is there. It is automatically it is there. Sometimes the people feel it that whether it really begins, whether it will really eliminate the need for signal processing. But no, so the answer is very, very clearly no, because the main problem is that it requires that much data, a lot of data. It may be applied in some areas, but remember the edge of the signal strengthening is very, very specific. It is very pinpointed. So it can never ever replace the signal processing. It will support only. We can verify it. Because and another problem is that it requires a lot of process. Lot of processing is required there. Lot of time, computational resources are there. That is also becoming a problem. So that is that. What is the difference between machine learning and AI? The only difference is there that here in machine learning it is the normal features. Here we see the graph-based feature, graph constructed. Otherwise it is the so this is one of our published works. What has been done here, that brain tumor detection by HOG and the FOS feature fusion with LDA and SNP. So when see there is a asymmetry in the data, you use the smooth. For example, you will see the case. For example, when training part and the testing are basically not the same, then you can generate the extra images, extra cases using the smooth. It basically brings out the symmetry. So here it is against different views are shown there. Samples of brain tumor images, it has been there. Then the brain tumor, you basically need to identify tumor. Where is it the problem? So in deep learning technique, large data set raises the cost and complexity of computing, while here it was a novel feature fusion technique with boosting classifier. As I told you, it is basically the imbalanced data set, while here we balanced it by a technique called a smooth. A smooth is a synthetic minority oversampling technique. It is used to balance the majority class and the minority. Another problem was their absence of explainability and transparency in predictions by the model. Here, SAFE, simply additive explanations, values are used to find the importance of the feature. Here it is the issue of overfitting, and here it is a linear discriminant with 5-fold cross validation. What methodology has been followed? It is basically brain MRI images are there. We do the pre-processing, we basically resizing, RGB to gray, median filter, and then HUG feature, then FOS feature, feature sampling using a smooth and feature reduction using LDA, then classification using GBX, GB light, GB cat, and then tumor or the non-tumor. What that we have to check out whether something is like say tumor, whether is it really the tumor or not. The methodology has been discussed here. So in Kaggle basically 253 data, total MRI image 253 breakdown into two category class 1 155 images, class 0 98 images. MRI scan modality is T1, T2 and flare. Again, see these are the view only. How much is visible is basically the different type of view. All images are provided in the Excel. Here it has been. Now, when you selected the data set, now the comes part the pre-processing. So, one of the important part of pre-processing is basically the images are resized into some standard size. It is, you can take either of them as per your needs. So here it has taken 512 by 512. Definitely, where you are able to extract out the feature and it shouldn't be too large. Then clip limited adaptive histogram equalization is used to enhance the contrast of it. The images are converted from RGB to grayscale and 3 by 3 median filter is used for denoise. Figure 6 basically describes about the pre-processing phase of the image. Input image is there where white part is basically like the tumor, resized image is there, then enhanced image, then RGB to gray, and then the denoised image. An HOG is basically feature descriptor that captures the structure, shape, and gradient information in an image. As we told that the histogram is all the oriented gradient. In any image, orientation by the oriented gradient, you can uniquely represent it. So what is shown here, it is compute gradient magnitudes and orientation for the image. Divide the image into cells and compute a histogram of gradient orientation within each cell. Remember, cell is like a pixel. It can be a one pixel. It may be a group of pixel, 2 by 2, 3 by 3, 4 by 4. That can also be the cell. Normalize histograms across overlapping to enhance robustness to lighting and contrast variation. Concatenated normalized histograms to form the final picture vector. What has been shown here? It is cell size, it is block size is given, number of features. The more you go into the detail, 16 by 16 and block size is 1. So, more number of here features are there and here accuracy. Methodology 5 is specific FOS feature minimum maximum standard deviation mean and median values are computed for each image. Bar chart representation of FOS features are there. So how what are these? These are basically statistical parameters, right? So mean value, median value. Because see, feature sometimes may be large, sometimes it may have the large length, but it may not exactly represent the reality what you want, not represent the picture what you are expecting. So in that cases, statistical parameters become very useful. Mean value, median value, standard deviation, minimum value, maximum value. And so their combination makes the things very clear. What is this KMN? It is denoted as image pixel intensity. In the total pixel is represented as N that we already. Featured sampling using the data set employed in this study is unbalanced. unbalanced. As you have seen, it is 155 and 98. That's why it is unbalanced. With more tumor images than non-tumor images, which may cause bias in favor of the majority class. So what is the solution? Solution is simple one: synthetic minority oversampling technique. It follows basically feature extraction in order to difficulty. It improves the model's capacity to acquire broadly applicable features. By interpolating between pre-existing samples, it generates synthetic samples for the minority class. After smooth, the tumor images remain same as 155, while non-tumor images increase from 90 to 155, balancing both cases. So before sampling, this was the case here from 198, and thereafter it is both are. So now coming to the methodology. The combined HUG and FOS features resulted 761 features, which is high dimensional feature space. To reduce computational cost and prevent overfitting, linear discriminant analysis is used for density reduction. To reduce the feature set, it entails projecting the initial feature space onto a fresh set of dimensions referred to as discriminants that have been specially designed for class testing. The eigenvalue decomposition of the scatter matrices, which measure the variance within and between classes, is how this is accomplished. Optimal separation between the altered features is ensured by LDA, which chooses the directions that optimize the proportion between within class and interclass variation. So key performance indicators for the classification task, as we also discussed in our earlier slides also, that it is accuracy, it is precision, it is recall, it is F1 score. They are based upon the basically false positive, true negative, true positive. Area, and now we come to the result part. Area under the curve of all classifiers is shown in figure 3, and safely additive explanation is represented in figure 4. So here actually it's some confusion. It's actually figure 9, ROC curve of all classes. It has been shown here. And the shape is basically it is a figure 10, not figure 4. So here it is there. It's our value. So it is safe value CAD boost classifier is also there. Comparative analysis, when we have applied the algorithm, our algorithm HUG plus FOS, and compared with a given one, what did we observe? That here our accuracy is a good one in compared to the other one. When we use the same Kaggle data, 253 value. So conclude future scope in this art. So in this article or in this work basically, as which has been written by Suman, lower feature fusion technique is forced for tumor detection. For image enhancement, contrast limited adaptive histogram equalization is applied and a median filter is used to reduce noise while preserving it. Features are extracted using HUG and FOS and then reduced using LD. Smooth techniques has been used to balance our data set to address overfitting. Five-fold cross-validation is implemented. The reduced features are fed into various boosting classifiers. Whenever overfitting is there, you need to take the more data. You need to cross-validate it. The experimental results indicate that the CAT boost classifier outperforms the others, achieving an accuracy of 98.3% and an AUC of 1. Future research will contain Future on expanding the multi-class classification and improving the model's accuracy by investigating other future techniques. So 98.3 is a fairly a good one. You also notice that at this time, our emphasis on basically dealing with the data. We are not bothered that whether we are able to apply GSP or not. But because initially you need to familiar with their data, that what values are there, how they are coming, where, what are the other issues. GSP is in the last one. On the other hand, HOG and FOS fails to capture spatial interrelations. That's why we explored MRI into using graph signal processing techniques to enhance performance of brain tumor detection. So this is the another work. The earlier one and the last work, what did we do? So now we move to the problem. Enhanced brain tumor detection in MRI with feature fusion and smooth optimization technique. So what did we do here in deep learning? It is large data set, imbalanced data set, less accuracy in ML classifier. So here we propose a novel feature fusion technique with gray level co-occurrence matrix and first order stress. What are first order? Again, like the mean, mode. Synthetic minority oversampling technique is used to balance the majority class and the minority class. Optimizing hyperparameter using great search optimization and gray wolf optimization. So here the images are there. Here views are given. What is given here? If you see here, it is sagittal view. So image processing is contrast enhancement, skull stripping, RGB to gray noise reduction, and then we apply the gray level co-occurrence matrix plus FOS, and then we use the future, and then using the feature sampling, and then you use the hypertube parameter using GSO, GW, which lead to the classification. Brain tumor, I think. So here data set description, it is the same data set which we have been already balance it. Scans, how the scans have been acquired using fluid attenuated inversion recovery. T1 weighted and T2 weighted sequences in the axial. In pre-processing, what you are going to do, generally the visibility of fine details of biomedical images are low. So clip limited adaptive histogram equalization. If you recall, see in our first slide of image processing, during our histogram equalization, we are able to basically enhance the image. So here also enhance the contrast of the images from the clay. It is clip limited adaptive histogram. And then the thresholding method with brain mask is used to remove the skull of the brain. The images are converted from RGB to grayscale, and a 3x3 median filter is used for denoise. This has been shown the brain tube so that you can see the different images are taken in mask, skull, median. Feature extraction, gray level co-occurrence matrix, and first order statistic techniques are used to capture both textural and statistical features. Here it calculates the spatial relationship between pixel intensities in an image, then assessing the texture changes, then 6 GIF and features we have calculated, Here capture statistical information about the distribution of intensities, measuring tumor intensity property. 5 FOS features are also there. So this is about both the things, both the techniques which we are using. So coming to the gray level co-occurrence matrix, each element represents the frequency at which a pixel with gray level I occurs adjacent to pixel with gray level J. Adjacency can be defined in terms of directions. For each pixel, look at its neighbor in a defined direction and distance. Count the number of times each gray level occurs. For example, 1, 2 is there, how many times it is occurring. Normalize the matrix to convert counts into probability. Because finally, we have to put into another matrix. So these are the parameters which you can find out from the or parameters of the features from the gray level co-occurrence matrix, contrast, dissimilarity, homogeneity, angular second moment, energy, correlation, FOS. So 5 specific FOS features, minimum, maximum, standard deviation, mean and median are computed for each image. Mean value we calculated, median value. That's how we can calculate it as kn plus 1 upon 2, km and n plus 2, km, n upon 2 plus 1 when n is even basically, that is divided by 2. So in the standard deviation, it is shown here equal to kmn minus mean value, minimum value, you are taking minimum thing. So this is the one. Kmn is basically the pixel, image pixel intensity, and the total pixel intensity is represented as. So again, see, we apply this smooth here as we are applied. What is the advantage? The advantage is the one our data bank they are normal. So in the data splitting, it is what is the ratio? It is 80 to 20, 70 to 30. We have taken 80 to 20. We have taken a classifier, support vector, machine random for a gradient boosting. To optimize the hyperparameters of ML classifier, to optimization techniques, grid search optimization, gray wolf optimization. What is the gray wolf? Here see it is the genetic bio-inspired algorithm. It is initialize the parameters of ML classifiers, evaluate fitness. First find first, second, and third best solution. Update position, calibrate the new fitness value of the new position, store the best. This is the so this is the flow chart of GW. Key thing is there that it is results and discussion. It has been shown here that it is when with the different transformers. So this is the it gave 0.68, 0.68, but when you use the combination, it is far better. It is 0.74. And in the random forest, it is 0.72. And then GLCM plus FOS, it is 0.76. So finally, it is basically the discrete transform, which gives the result better than the. So experimental result with GSO, experimental result with GW. Here it has been shown here. So here again you see that the or whether some tumor is actually there or it is basically a false image. That section has to be carried out. So here it has been shown that accuracy is highest in the GB, in the SEM, and in the GWO, the highest value is basically 0.9. What you are seeing, this basically a convergence curve. So this is, and on the right side it is ROC. ROC basically tells you that how much does it take with our algorithm, with our instruction. Now coming to the comparative analysis. Comparative analysis. So when we have applied our method of this machine algorithm to the feature extraction method, so this is our result, and our results are clearly better than the other techniques. Like in the Kaggle one, our GVGS method performs the 80, allowing 84%, and GW it is 89%. So here conclusion and future scope in this article in novel feature fusion technique for tumor detection or image enhancement. We have used basically clay, contrast limited adaptive histogram equalization, and media filter. Features are extracted using GLCM and FOS, and the smooth technique has been balance of data set parameters. So ML classifiers are optimized and to do optimization. The experiment indicates that the GB cluster outperformed the others, achieving accuracy 89%. The AUC of 0.89. So we just changed the. So this is the one. So just wait for it. 2-minute break for a session change. Just be there. बैठ जाइए आप